grad student here at Steward Observatory at the U of A, and I'll be your host this evening. Space Drafts is Tucson's chapter of Astronomy on Tap, which is a worldwide organization bringing astronomy talks to pubs and breweries just like this one. If this is your first time at Space Drafts, you may have noticed we are right next to an active train line, which means one or both of our speakers will almost inevitably be interrupted by a train in the middle of their talk. And whenever that happens, we all like to raise our glasses and yell choo-choo in an effort to appease the train gods and hopefully prevent them from sending us another one. Let's see what else. The show is going to be two speakers tonight. Talks will be about 20 to 30 minutes each. We'll have a 20-minute intermission in between, during which we invite you to check out our merch table. We have lots of lovely things you can buy: stickers, magnets, postcards, posters, all sorts of stuff, pint glasses. So please check that out. We also have a donation jar if you like the show so much that you're inclined to donate. The more merch we sell, the more merch we can buy. So let's see. Please don't forget to tip your bartenders. And I think that's about it. So with that, I'd like to introduce our first speaker, Haowen Zhang, who's going to tell us about supermassive black holes and how we study them. Thanks.
All right. Hi, everyone. I am Haowen Zhang. So I'm currently a fifth-year graduate student of the local Steward Department of Astronomy. So, okay, so how do we get this one?
Oh, wait.
No.
Hang on.
Frozen?
I'm trying to select.
Now. You might have to point it more at the...
Yeah.
Oh, where did it go? Hang on.
Oh no. Yeah, you moved it.
Sorry. I don't know what happened. I swear I just like touched it.
The window.
Do you want to jump in?
Yeah, I can't see. No.
Is it that window that needs to be dragged over, I think?
Oh, is that the actual window?
No, that's the OBS
it's
window.
not.
So it resized when it came back over.
Oh crap. Sorry.
And this is the back, so I don't know what to do.
Sorry, everybody. Wouldn't be a Space Drafts without some technical problems at the start. I'm just gonna reproject it.
Bring your mouse over, and then
Where's the window?
All right, so just in the meantime, so today I'm just gonna basically talk about supermassive black holes. Mostly how we study them with observations with telescopes.
Where is it?
But actually, I am a theorist, which means that I don't do observations myself, or I don't even process observed data. Instead, I try to come up with theoretical models to understand what we're really seeing in the observations and how to explain why we see those huge monsters in the earliest universe, especially with the most recent results from the James Webb Space Telescope, which is a $10 billion telescope that got delayed for many years.
That's what happens. It doesn't.
It just brings it back.
Yeah.
What the heck?
I don't know.
What the heck?
I have no idea.
I swear I did not do anything aside from what you had showed me that you had done.
Okay, nuclear option.
Yep, nuclear option.
It still says it's coming through.
Okay, so since the stream is running,
Start telling jokes.
Come on, computer. Where's my mouse? There it is.
I try to click her right now.
There we go.
Alrighty. 1 sec.
Okay, try it
One
now.
sec. Does it need to be
You might have to refocus
How about now?
that one. There we go.
Yeah.
Cool.
Okay. I think it's working.
We're off the
Great.
races.
Alright. So, yeah, supermassive black holes and how we study. First, black holes come in a huge range of masses. So, yeah, I'm not sure if you can see it, but on the left-hand side we have these stellar mass black holes, which are typically tens or up to 100 solar mass being the mass of the sun. So they're just typically remnants of dying massive stars after explosion. On the other side of the scale, we have supermassive black holes, which are really the focus of this talk. They are typically at least 1 million solar mass, which is really huge, but they can get even more massive. Above 1 billion solar mass, even in the early universe. So it is, as of today, still a mystery why we see those huge monsters in, say, since the within 1 billion years since the Big Bang of the universe. Embarrassingly, we don't know as much about the middle of this mass scale, which are intermediate mass black holes. But I guess we don't have to worry as much because it is not really the main focus of today. So, okay, black holes are supposed to be black, right? But the fact is we have detected so many of them. So how do we do that? Basically, we start with the simplest case, the easiest case, which is if we have a supermassive black hole in our backyard. Backyard meaning the center of the Milky Way, which is already like 30,000 light years away. But cosmologically, this is really our backyard for human beings. Okay, so what we do is that because this black hole is so close to us, we can actually see so many bright stars moving very fastly around the central point of our galaxy. So if we measure how fast these stars are moving and how far away they are from the central point, with the help of Newton's laws, or Newton's dynamics, we can actually figure out the mass that's enclosed in this tiny central part of our galaxy, which turns out to be 4 million solar masses. And with such a big mass, enclosed within such a small radius, nothing can be there except for a supermassive black hole. So even though we cannot see the black hole itself, we can see how fast things are moving around it. And that's how we find out that there's a black hole. Okay, so this is the backyard. Things are close enough so that we can see them. What about the galaxies that are really far, far away? You don't see a thing here, right? That's exactly the idea. I just basically downscale, like zoom out by maybe 100 times of the plot here to basically simulate what astronomers can see for galaxies that are far away. What we see here is exactly that we cannot resolve anything that's close to the black hole that's in the center of this black dot. So, in other words, we cannot just measure how fast the stars are moving around the black hole here, and we cannot see, or we cannot tell whether there's a black hole. But it doesn't mean that we're just out of luck, because what we're talking about here are the black holes that are really black. In other words, they are not actively growing and not giving out any photons or radiations. But things are different when the black holes are growing or basically sucking in gas or even stars to grow in mass. And this is something that we call accretion in astronomy. And when black holes are growing by eating lots of gas and stars, there are actually lots of structures that are forming around it. So first of all, the most extended structure are these jets, which are directly launched right off the black holes, carrying lots of electrons and lots of radiations. So that's some signature that astronomers can try to catch with telescopes. For example, here we can see these red and basically symmetric jets shooting out, even like extending out of the whole galaxy where the black hole is living in. And just by seeing these jets, we can be pretty much sure that there's got to be a black hole that's driving these jets. Yeah, so extended jets. And the only twist being that this is actually not captured in visible light wavelength range. But instead, this is a image in the radio wavelength. In other words, we're not using something like Hubble Space Telescope with big tubes to capture these images, but instead we're using big dishes or radio telescopes. If we just take a look at the images, these photons from the accretion disks actually make the whole black hole look like a star because it's outshining the galaxy that the black hole is living in. So okay, it looks like stars. It is very bright in the ultraviolet to the visible light regime, and it comes from accretion disks. Okay, so because of this morphology or this appearance, astronomers creatively name these objects quasi-stellar objects, or in other words, quasars. So if you check out your Google map and search quasars, you can actually see a quasar street somewhere in the southern Tucson, I think. So I strongly encourage you to try that because I think there's another street called Sirius, which is the brightest star in the sky, that's crossing with the quasar street. Okay. So this is basically the signal from the accretion disks that's telling us that there must be a black hole. Okay, so if we go even further inside, we'll actually see an even smaller structure, which is called event horizon. So basically, the thing with event horizon is that no photons can escape from this scale or this edge of the supermassive black hole. So in principle, we should expect to see totally darkness within this event horizon. And this is very small. I think the event horizon of this particular black hole might be just like a few pixels on this diagram, but it's actually the holy grail of this whole black hole detection game, because it is the smoking gun evidence of a black hole or a supermassive black hole, because as long as there's a black hole, there's got to be an event horizon according to the general relativity. So it would be great if we can have a big enough telescope to see those fine structures, to fully prove that we must be seeing a black hole instead of anything else. So quite a few years ago, we finally have that capacity, or have that these kind of facilities by basically connecting many radio telescopes around the globe to build a radio telescope that is as big as the Earth, so that we can see the event horizons of supermassive black holes in nearby galaxies. So here's the image. It looks like a donut. There's a dark part inside of it. That's what's making this thing look like a donut. And this darkest part is just the event horizon that I'm talking about. So no photons can escape from this event horizon. That's why it appears dark. But there's some accretion going on, like right outside of it. So that's why we can see this bright part of the donut. This basically fully proves that, without any doubt, there are supermassive black holes in our very own Milky Way and in another very massive, very big and nearby galaxy called M87. But that's pretty much just it, because although this Event Horizon Telescope is very big, there are not many objects that are close enough or having big enough black holes for us to see the image so closely and so clearly. So using this telescope, we don't expect to see many more supermassive black holes in the nearby universe. Okay. So if black holes are not nearby, they're not big enough, they cannot be seen by our telescopes, they're also not bright enough, they're not actively growing, they're not giving out enough radiations. I guess our last resort would be to hope supermassive black holes are about to collide with other supermassive black holes when we are trying to detect them. This is because colliding black holes, they create gravitational waves, which are basically just these tiny wrinkles in the space-time when they are orbiting around each other and finally colliding. So you can see the waveform here corresponding to these wrinkles, and after the black holes collide with each other, the gravitational waves just dies down, and the residual waves just propagates in space for us to detect. So this video basically shows what's happening with the in one of the detected systems for detected black holes using the LIGO detector, which is basically two separate detectors separated very far away in the United States. But the current LIGO detector is designed to detect smaller black holes, for stellar mass black holes, which are tens to up to 100 solar mass. This is like very much smaller compared to the supermassive black holes, which are like millions solar mass. It also, the LIGO detector also has a detector size of about 4 kilometers, and which is, by the way, 2.5 miles in imperial units. So, okay, so now I guess trivia question: what detector size is needed for detecting supermassive black holes, which are above or at least 1 million solar mass. So I have 4 options here. First of all, 4 meters, 12 feet. Second one, 4 kilometers, 2.5 miles. This is basically the same as LIGO. The third one is 4,000 kilometers, which is very similar to the Event Horizon Telescope that we use to detect black holes in the Milky Way and M87. The final one is a bit crazy. It's 4 million kilometers. Okay, so I encourage you to make your guess, even though you may not know the answer. And whoever gets the right answer, please just come forward to claim a sticker or a postcard after this talk. Okay, so the one back there, yeah. Okay, yeah, so it is correct. Okay. So we also know that the size of the Earth is about like 10,000 kilometers, right? So this is basically 400 times bigger. This is 400 times bigger than the size of the Earth. So we're never gonna be able to build it on the Earth itself. But people actually came up with very creative and admittedly very crazy ideas just by building it in this space. So what we're proposing is that this blue dot is the Earth, this yellow ball is the sun, and we can see these 3 detector array basically trailing the orbital motion of the Earth around the sun, just like flying a kite by the Earth. So what we're gonna do is to basically detect or measure the stretch or the shrink of the distances between these 3 detectors when they're moving so fastly around the sun. But amazingly, I think the Pathfinder program of this detector is going pretty well. So I hope, this is definitely not happening in a decade, but I hope that they can make some actual measurements or detections before I retire so that I can write some papers about it. Yeah. Okay. So basically, to summarize, how to see supermassive black holes with telescopes or any other detectors. We need them to be, we need the black holes to be either close enough, like the one in our own Milky Way galaxy or in the M87, so that we can either trace the stars that are orbiting around the black holes or just directly resolving or detecting the event horizons using huge telescopes. The other option is that we look at bright enough supermassive black holes. For example, they may be bright by showing jets in radio wavebands in radio galaxies. Their accretion disks could be bright because lots of gas are getting heated, so they just look like stars or appear as quasars in the real images. And if neither of these applies, the last resort will be to hope that we are seeing the black holes that are colliding with each other so that we can detect the gravitational waves, again, which is not happening in the next 1 or 2 decades. Okay, but the problem is, what if we want to study all the other supermassive black holes that are far away, that are not accreting, that are not growing and bright enough, and also not colliding with other supermassive black holes? I'm afraid at this stage, real observations, they do not help as much. So here comes the theorists. And instead of trying to see those supermassive black holes, trying very hard with our telescopes to catch 1 or 2 photons, we try to simulate them, definitely not with real telescopes, but we have these fancy and bulky, expensive supercomputers, or supermassive computers. Basically the way we do it is that this is kind of like doing numerical simulations. It's kind of like, personally, I think it's kind of like slow cooking. So we have all these ingredients. We have stars, we have supermassive black holes, and gas like hydrogen and helium. Okay, and then we dump all these ingredients into these expensive pots. We start the simulation, we wait for a long enough time, because simulations, they typically take very long to run. And at the end of the simulation, or cooking, we remove the lid and we pray that the results would match our expectations. So what do I mean by matching our expectations? Well, we just look at the end result of the simulation, and we hope that the properties of each of these individual galaxies and black holes match what we observe in the present-day universe. But even though we calibrate these simulations based on the present-day universe that we see from the observations, the simulations actually contains much more information than that, because we can actually see the individual histories of each single galaxy and black hole, which we're never going to be able to do with real observations, because in real observations we only get to take snapshots of different galaxies at different times. We don't even get to trace the same galaxy across their evolution histories. And specifically, if we look at what's going on with the individual galaxies and black holes, we can get these videos showing exactly how these supermassive black holes are driving gas out of their galaxy and affecting the growth of both black holes themselves and also the galaxies that they're living in. So we get much more information compared to what we get from the observations, even with the fanciest telescope like James Webb Space Telescope. Okay, so in order not to make all the observers here unhappy, I'll then talk about some problems with the simulations. So simulations are they perfect? Absolutely not. One particular problem that I've been thinking about recently, and also many other theoretical astronomers have been thinking about, is that if we look at the supermassive black holes in the simulations, they seem to be like this blue cloud represent the simulated black holes, and if we go further, like in this vertical direction upwards, we get more. We basically get bigger supermassive black holes, and these gray dots are the actual black holes that we get from the observations. So it seems that from the simulations, black holes are having trouble growing sufficiently to match what we see in the real observations in the early universe. So what could be the reason for this? Unfortunately, theoretical astrophysicists and observers, they do not have a well-established answer for this. My personal guess, firstly, maybe the simulations are too small in size, because there's always a finite capacity of current supercomputers. Even though they're supercomputers, you can only make so big simulations instead of making them even bigger. The other thing could be that maybe, sorry, okay, it's not working. Okay, never mind. The other thing could be that black holes in the simulations may be just pushing away too much gas from their galaxies so that they don't get enough fuel for sufficient growth to grow into objects that like we see in the real observations. But apparently, lots of people have different opinions. As I learned again from the JWST conference last week in Boston, and I guess this is currently a very active area of research. So I would like to basically stop here, stop talking so that I don't piss anyone off, just in case. Yeah. Okay, so finally, a few take-home messages. Firstly, how do astronomers see supermassive black holes with telescopes or other detectors? These black holes basically have to be either nearby so that we can see the motion of stars around the black holes, or directly detect the event horizons using giant radial telescopes. Or they have to be bright enough so that we can just detect their jets or accretion disks in different wavebands. And lastly, if neither of these happen, we have to pray that the black holes are colliding with each other so that they provide gravitational waves for us to detect. Of course, to detect in the future. For the rest of the cases, we cannot really see them, so we will have to simulate them. By simulating galaxies and supermassive black holes, compared to observations, we can know exactly all these different properties like positions, masses, how fast they grow, and the growth histories of each individual, every single galaxy and black holes in the simulation. However, it also comes with problems like simulations are not matching every piece of observation that we see at different era of the universe. And yeah, I think observers and theoretical simulation people are just working together to solve these, to basically solve this question. It's actually a good thing, like a concluding remark, it's actually a good thing, I think, to have these problems, because as a theoretical astronomer, we actually need funding. So basically, wherever there's questions or problems, that means fundings and jobs, hopefully permanent jobs. Yeah, so personally, I'm very hopeful that I get to work on these problems and I can get some funding. Yeah. All right. So yeah, I'll just conclude here, and thank you so much for your time. I'm happy to take questions. Yeah. Thanks. Okay, great. So I think this is because if you have way bigger supermassive black holes, you need basically the frequency of the gravitational wave that they're emitting is much lower, which means that you need a much larger separation between different detectors to capture this kind of signal. Basically, you need a much larger space between the detectors to for these difference to accumulate, so that you can tell the difference due to the gravitational wave. Yeah. So that's a really great question. I think basically it's the sheer I would say it's the sheer excitement to imagine what's really happening around the black holes, because that's it's a really high energy configuration, because you will see lots of radiations and also very spectacular things, because that's not very intuitive because that's the lights, the light rays actually get deflected around the black holes. So that's really amazing to me. Yeah, right.
All right.
Right. I guess that's it.
All right, thank you, Haowen. All right, so we're gonna have a short intermission now. So feel free to go get another beer. Don't forget to tip your bartender. Please check out our merch, and we'll be back in about 20 minutes. So we'll call it, I guess, 8:25. Cool. Thanks.
Unmute. There you go.
There you go. And then click there.
The MacBook
Back there.
thing.
Should be
The MacBook touchpad scares me.
Yeah.
2023 is the time currently. Both up there? Yeah, we got both up there. Mike and Brother. Hello, microphone.
I'm loving the wireless mic.
Oh, so good.
So nice.
So good.
What else are you doing on Tuesday? Make it a thing to come.
I'm just gonna adjust the.
All of it. Yeah. Yeah. All right. Yeah.
Good to go? You want me to put in the Slack or resetting the camera?
No.
Hold your britches.
It's fine. It doesn't.
They land. What is it? Rapid disassembly.
It just
Yeah.
Rapid unplanned disassembly.
Perfect timing.
All right, welcome back, everybody. It's time for our second talk of the evening. Sarah Moran is going to tell us about Strange New Worlds through the eyes of JWST.
Thank you. Thank you all for sticking around. So you may have noticed I called it JWST here. That's just because I think about it all the time, and so I don't like saying its full name out loud. So I'm going to call it JWST, but it means the James Webb Space Telescope. And I've also called it Strange New Worlds. Hopefully some of these worlds are pretty familiar to you, but you'll be seeing them in a new way. So just for some context, I always like to show just how big JWST is, because I don't know that people always appreciate it. So this is a 2-scale image, where that little image of a person there is me. So the height I am, 5'4", scale that up, and that's how big JWST is in space on the other side of the moon. And although JWST can take images, the primary workhorse is actually through something called spectroscopy. And that is something that maybe sounds scary, but you are actually very familiar with. So if you've seen that Pink Floyd album, that's all that's happening, is white light is coming in and we're separating it into its constituent colors. So just breaking it up into all the different parts of the rainbow and measuring the signal at each color or each wavelength. If we turn that into something more graphical, it looks like this. And so these are all the different wavelengths of light, from gamma rays, which are the shortest wavelengths of light, all the way out to the radio, which is mostly what we heard about in that previous talk about black holes. Because they're so big, to measure them, you need really, really long wavelengths of light. What we care about for this talk is right in here. And so this tiny little sliver here that's highlighted here is the visible, which is what we can actually see with our eyes. That's important to note because every other image I show you of actual data from JWST is all out here in the infrared, where our eyes cannot actually see. And so all of these are actually translated from the data we take from the telescope into something that kind of means something to us when we look at it with our eyes. The other thing I want you to notice here is this tiny little region here, a little bit into the ultraviolet, just a little bit bluer than we can see, and a little bit into the infrared, just a little redder than we can see, is the domain of Hubble. The Hubble Space Telescope is still on sky, still doing amazing work. You're going to see a couple comparisons throughout the rest of this talk, but I never want people to walk away with the idea that Hubble is somehow inferior to JWST. It's doing different things. It's giving us complementary information, because it's going further into the blue, and it's also set the stage for a ton of the work I'm going to talk about. But JWST, of course, has access to all of these wavelengths out here, where there's a ton of information about all kinds of chemistry and dynamics happening on other planets. So this slide is showing in roughly visible light, roughly what we would see if we were able to go to each of the planets in our solar system and see them with our eyes. So in turn here we have Venus, and of course immediately I'm lying to you, Venus doesn't look like this in the visible. is kind of just a blank white ball. This is enhanced at the ultraviolet so that we can make out the clouds. And then we have Mars, sort of dusty red, Jupiter, Saturn, Titan, which for the purposes of this talk I'm going to call a planet because it has an atmosphere and I think it's cool, so it's a planet. It doesn't matter that it's a moon. This is Neptune, and finally Pluto, same moons above. I don't care whether it's a planet, I'm calling it a planet. You know, I've never gotten applause on that before, but thank you all very much. So this is what we would see if we went to these objects. It's a very different story with JWST. So we're starting roughly in order here from closest to us to farthest away. And we are unfortunately having to skip Venus because it's pointed toward the sun, and we can never point JWST at the sun because it would totally fry all of the instruments, and we don't want to do that. So we unfortunately can never look at Venus, but we can look at Mars. And so we get information like this. What we're doing here is looking at what's called thermal emission. In other words, temperature. So we're measuring the temperature across Mars with all of, at this particular wavelength of light. And so what we can see here is that this really strongly illuminated part, it's really bright, it's very hot. So that's the part that the sun is in. And then this darker part here is what's night on Mars. It's not groundbreaking, but I want you to keep that in your head for later when we go much further outside the solar system. It's going to be important. The other cool thing here is this darker region here, which is Hellas Basin. And it's darker because it's cooler. It's cooler not because sunlight is not hitting it. It's because it's deeper. It's a canyon, sort of, or a crater on Mars. And so there's more atmosphere in the way, and so not as much sunlight is bouncing back to JWST to measure. So we're essentially seeing through just a little bit more atmosphere, which makes it cooler when we take that measurement. Next, moving further out, we see Jupiter. So if you have looked through a telescope at all from Earth, you've hopefully seen Jupiter through a scope, and this is not that crazy to you. We go one step further and start labeling the different things in this image. What I really love most here is you can see this very faint shadow here. That's one of Jupiter's rings. I hope most people know here that Jupiter has rings, but that's not necessarily the thing you think of when you think of Jupiter. Of course, here we have the great red spot. It's really bright because it's also really hot. What we're doing here when we have all of these different colors is we're taking measurements in different wavelengths of light, which means we're reaching different altitudes in the planet's sky. So we're measuring different cloud layers and different dynamics across the planet. We can also see all of these little moons out here that are glowing. This sort of bright spray at either pole are the aurora. So maybe you've seen aurora on Earth. Almost every planet in the solar system has that as well, and we're able to visualize them here, both with Hubble and with JWST. So that's illustrated here. Again, just to remind you, this is roughly what we would see with our eyes, and this is Jupiter as seen by Hubble, and that's compared to what we're seeing with JWST. So you can see a lot of the same features here, these bright bands of clouds, and then maybe we're seeing a little bit deeper with these darker bands. This is not actually what you would visually see. This is enhanced in the ultraviolet with those strong aurora. Again, complementary information. My pointer has stopped working.
Oh, sorry.
There we go. I love showing this image because it's actually not a science image at all. This is one of the very first images that JWST took, and it was doing it purely as a calibration test. They were just pointing at a really bright object. Jupiter is close, so it's very bright. And just kind of putting the telescope through its paces, making sure everything was working properly. And yet we get this stunning image out. And the thing I love most, this thing right here, is actually Jupiter's moon Europa. And that black spot in the middle is because it's so bright. It's covered with an ice layer on the outside, and so it's so bright that it's actually saturating this detector. So that black spot is just because there's too much light for the detector to take in. The coolest part, though, to me, is this tiny little dot right here. That is actually the shadow of Europa being projected onto the cloud tops of Jupiter. If you don't think that's the coolest thing you've ever seen, I don't want to talk to you anymore. And again, this is not a science image. This is just like, oh, let's point the telescope and see what happens. And you get this nonsense out. It's crazy. So we don't yet have images of Saturn from JWST, so I unfortunately have to skip it. I'm looking forward to those, I hope you are too. But instead we have Titan, which is the largest moon of Saturn. Titan is a super cool planet and moon because it actually has a really thick atmosphere. It's actually 1.5 times as thick as Earth's atmosphere. But it's very from the sun, so it's very, very cold. What we're looking at here on the left is a single filter from JWST on the NIRCam instrument, which is actually built just down the road at U of A. And this bright spot here you see in the top is a cloud. So not only does Titan have a very thick atmosphere, it has an active cloud and what we would think of as a water cycle, but it's too cold for water, and so it's instead a methane cycle. Something that's a gas here on Earth is cold enough to be part of this cloud cycle of vaporizing and then raining back out of the atmosphere. Titan is also very well known because it has a very thick haze layer, which is what you're seeing illuminated here. On this right side, we're now seeing multiple different filters combined, multiple colors, multiple wavelengths. And so we're seeing kind of similar images. We see this bright cloud. This dark region up here is Kraken Mare. That's actually a lake on the northern pole of Titan. And again, it's much too cold for a water lake. Instead, this lake is made of ethane and methane. When those images were taken, the team got really excited, so immediately alerted a ground-based telescope, Keck. So this is not JWST on this side. This is from a telescope in Hawaii that has very fancy optics on it that can actually make these kind of measurements. And they're not going to stare at Titan the whole time. They have lots of other science to do. But because this image was taken, and we could tell the Keck team, hey, there's this cloud here, we want to see it, they immediately imaged it again just a few nights later, and you can actually see it's moved across the disk. So we're actually tracking cloud motions on this moon in the outer solar system. This is another moon of Saturn. Saturn kind of has all the best moons. I don't know how it got lucky that way, but it has all the coolest moons, including Titan and Enceladus. So Enceladus is this object is as imaged by Cassini. This is not what JWST saw. So the Cassini spacecraft was actually a probe that went to and orbited around the Saturn system for a long time and got these beautiful images. You might just be able to see these jets at the bottom of this image, which is the south pole of Enceladus. So Enceladus is what we call a water world. It's enshrouded in a thick layer of ice, but underneath that is actually a salty water ocean that is able to stay liquid because it's salty, because it's protected by this layer of water ice. The interior is hotter. But some of that water is escaping through cracks in the ice at the South Pole. And that's what JWST was able to see. So this very, very bright pixel here is actually the disk of the moon. And all of this blue material here is water being spewed out of that South Pole. And so you can see, this is 1 pixel, this is many, many, many pixels. So this water is actually spraying out to about 20 to 40 times as much space, as wide as the moon itself is. And all of that water gets carried throughout the rest of the Saturn system. One of Saturn's rings, the E ring, is actually fed by this geyser from this tiny little moon. Next we go to Uranus. This is where I sometimes run into people. Raise your hand if you knew Uranus had rings. Most people, but not everyone. So yes, Uranus has rings, and they're beautiful. That's much harder to see when we don't have these infrared wavelengths like JWST provides us. This is what Hubble sees when it looks at Uranus. So you can squint and very vaguely see this outermost ring here, but they just pop out in beautiful contrast here when we're looking with JWST. The other thing you see here is Uranus is tipped on its side, and so this part of the planet right here is actually the pole, and you can see it's a little bit whiter compared to this blue. And again, these are false color images. This is translated into something that means something to our eyes. But this is actually a polar hood, is what we call it, on Uranus, and so it's this vast storm system on the planet. So now I'm shifting into a different perspective. This is still Uranus, but we're kind of zoomed out here. And so all of these little bright blue dots are moons of Uranus. These reddish dots are actually galaxies that are in the background. If I zoom out even a step further, I just like to show these because I think it really puts us like in our cosmic place. This, of course, is the very outer reaches of our solar system, and yet you see all of these very distant galaxies, which just makes me feel very, very small, and I like to appreciate that. You can see now that the moons are labeled, which leads me into my first trivia question. So I kind of intended for you to be able to read the moons so that maybe you could have a hint, but unfortunately you don't get that, so you just have to know or guess. So I'm asking you, what do we name the moons of Uranus after? And so you have options here. Are they named for Roman gods, for bodies of water on Earth, for Shakespeare characters, or for notable women throughout history? Raise your hand if you have an idea. You in the front here. Shakespeare characters, you are correct. So, if we could see these tiny little images, you would see that they're named things like Miranda and Ariel and Umbriel, which of course are all characters from The Tempest. I like to hide non-science questions in my trivia questions, just, to keep people on their toes. Okay, finally, our last object in the solar system that we're going to visit today is Neptune. Again, beautiful ring system. Did you know Neptune had rings? Yes, okay. That's more likely than Uranus for the most part. The other really cool thing you can see here is these bright spots here are all different clouds across Neptune. And again, it's much too cool for water clouds, so when we think about clouds on Neptune, we're thinking about methane again. And they're very, very bright in these images. And all these little dots here are, again, moons of Neptune. And you might notice that this moon and this moon in particular seem to be in the same exact track, the same orbit as the rings. And they actually are. They're what we call shepherd moons because their gravitational pull is helping shape the orbit of the rings. Again, now I'm showing you, this is from the Voyager 2 spacecraft when it actually flew by Neptune. So those are the kind of images that we could get when we sent something very, very close to the planet. Again, you see this beautiful cloud. Here's the most obvious one, but there's one here as well. And compare that to what we could see from Hubble. So you can kind of maybe make out some shades of darkness and brightness, but it's much harder to tell what's going on. Whereas when we look in the infrared, we just see these amazing cloud features pop out right away. So again, we're zooming out a little bit. Here's Neptune down here, here's one of the other moons. And then this incredibly bright, shiny object is actually Neptune's moon Triton. And it's just sending these diffraction spikes all over the place because it's so incredibly bright. It's covered in a layer of nitrogen ice. Again, very, very outer reaches of the solar system, very, very cold. The thing that makes up most of our air here on Earth is actually the ice, is made of ice, and it's covering the surface of this moon, which is very, very bright, which is why it just reflects all this light everywhere. Again, zooming out, you can see some of the other moons here that are much closer to the planet. Triton, you might notice, is quite far away, and part of that, we think, is because it actually didn't originate with the Neptune system. We think it was probably an object something more like Pluto that was orbiting a little bit further out and then got caught in Neptune's gravity and now orbits the planet, because it actually orbits the wrong way compared to the rest of the moons, which all orbit the same direction that Neptune rotates, but it orbits backwards. Again, just zooming out even more here to orient you. That's Neptune, that's Triton. These tiny little dots, which you maybe can't make out from the back there, are the moons. Everything else you see in this image is a galaxy. Okay, that is our very brief, quick tour of the solar system, and now we're going to start moving beyond. And so, when I talk about planets outside the solar system, we call them exoplanets. Exo meaning outside. It's a very brilliant name we've come up with. All of these images are just actually solar system planets that we've colored differently to make the case that they're different planets. None of these are real pictures, which is going to be important because all of these objects are very far away. Compared to the previous talk, we were talking about things, 30 to hundreds of thousands of light years away. All of the exoplanets we can measure are actually, relatively speaking, very close, but they're too far away for us to get these sort of disk-resolved images. Instead, we're looking at pinpoints of light. So this is kind of giving you a little bit of a sense of that, of where these objects are in space. So this is our solar system down here, and all of these little colored dots that are slowly being filled in as we go through time are the different exoplanets that we know about. And these different colors just are telling you how they were discovered, which is not particularly important to think about at this moment. So you can see they're all relatively close in our neighborhood, compared to things like, the center of the galaxy, where a supermassive black hole is, or outside the galaxy entirely. This is my second trivia question, which is science focused because we have to do something. So what is the name of the first exoplanet around a sun-like star? I have A, 51 Pegasi b, B, Ogle 2003 BLG 235 LB, WASP 39b, or TRAPPIST 1b? I can't see, okay, right, here. TRAPPIST 1b, unfortunately no. We discovered that in 2016, which is my first year of grad school. Fairly late in the game, really. Another guess, you heard right. WASP 39b, also no. I can't remember off the top of my head when that was discovered. You were here. No, I have no idea what you said, but it wasn't one of these things, so I cannot relay your joke to the rest of the crowd. I'm very sorry. B, Ogle, whatever, blah, blah, blah. No, I don't know how you say that one. We got there through process of elimination. Congratulations, everybody. I heard someone in the back table say it, and so you can claim your prize at your leisure. I don't know exactly who said it first. But yes, 51 Pegasi b was the first, what we call hot Jupiter, discovered around a sun-like star. We actually knew about exoplanets before we discovered this object, but they were around things called pulsars, which are not stars at all as we understand them, and so typically we call this one the first real exoplanet. And now you'll never forget that it's 51 Pegasi b. So I start with this image, which is actually kind of a cheat, because this is not at all what we normally see when we think about looking at exoplanets with JWST. This is what we call a directly imaged planet, which for the vast majority of exoplanets we know about, we are not able to do. We need a couple things to happen in order to make this kind of measurement. We need the object to be pretty young, so it's giving off a lot of heat, and we need it to be well separated from its host star, from its sun, in order to get the difference between the brightness of the star and the planet. That doesn't happen very often. In this particular case it did, and so I'm showing it to you because we were able to do it. But this is the last time you're going to see real images of exoplanets. The rest of them are all spectra, which I'm going to walk you through so no one panics. But first of all, let's look how pretty this is. So we're looking in different colors, different filters again, from JWST, of this object in the center, which is this planet. And there are a handful of more targets that we're able to do this for, but again, it's relatively rare. Instead, we use something called transmission spectroscopy, which is a terrifyingly long name, but you shouldn't worry about it, because all we're doing is looking at shadows. So I've kind of broken it down here in this image. So this, of course, is Earth, where we're standing, not scary. And we're looking in different colors of light. So we're going in and out of the ozone band at 9.5 microns versus in visible light when it goes to blue, and then back into a different wavelength of infrared light. And so as we pop in and out of the ozone band, you can see that the planet looks like it gets bigger. And that's because ozone is absorbing at that wavelength, and so we're able to detect it versus when it's not. The other cool thing about this image is this bright thing right here is actually Earth's moon. And you can see as we filter through all of these different wavelengths, it stays the same size. That's because there's no ozone on the moon. In fact, there's no atmosphere whatsoever. And so it stays the same strength of signal. So if we do that kind of measurement, it's there to remind you that graphs are not scary, and we turn it into a graph, we get something like this. So this is the amount of light we're measuring on the y-axis, and then the x-axis here is the color, or the wavelength of light. And all of these little bands are telling us different molecules that absorb at that color. So what we're looking at here, popping in and out of this particular band, is the ozone band, this really strong feature in this graph. And so that's all we're doing when we look at exoplanets, is measuring all of these different colors as the planet passes in front of the star, and saying, okay, there's a molecule that corresponds to, you know, in this example, ozone here, or maybe water here. And we're just playing that matching game with the shadows to determine what these planets are like. Every other image I'm showing you that looks like a planet here is an artist's image. And they are beautiful images, but they are not real. Again, not real, artist's image. Great job to the artist at Space Telescope. Not what JWST saw. So this is WASP-39b in an artist's imagination, which at this point is the best studied hot Jupiter planet. It's called a hot Jupiter because it's about the size of Jupiter, but it orbits so close to its host star that it's much, much hotter. So we very creatively have named that kind of planet hot Jupiter. So again, this bump here is telling you the absorption of a particular molecule in this planet's atmosphere. And so all of the measurements we've been able to make previously have not told us anything about carbon in planets. And carbon's a really important molecule if we want to know things about the kind of chemistry happening in these atmospheres. If we want to know how the planets may be formed. And so this very obvious feature, so these dots are the actual data that JWST measured, and then this colored blue line here is an atmospheric model. You can see it matches pretty well here. And so this is carbon dioxide. This is the very first time we are actually able to detect carbon dioxide on a planet outside the solar system. And I was really lucky to be part of the team that actually was part of making this measurement. And so I also am a theorist, so I don't sit here and analyze these data. I'm the one who makes the pretty colored lines and tries to fit the data to them. So my friend, who is a grad student at Johns Hopkins, was actually one of the ones who was really trying to get these data to look nice and for us to understand them. And so last summer, maybe a week into the first set of science data coming down from JWST, I was sitting next to him with apparently nothing better to do, watching him work at his computer to come up with this data. And I got really excited when he finally plotted it and we saw this here, because that's exactly what we would expect from carbon dioxide. And so it's the first time we'd seen this, and I got really excited, and other people kind of walking through the courtyard started gathering and going, oh my gosh, it's there, it's so exciting. Until we have this whole crowd around us. You might notice here, again, it's a little hard to see, there's a little bump in the data here that the model doesn't fit at all. And so after we got over our excitement, you know, like 10 minutes of, oh my gosh, we've seen carbon dioxide for the first time, we're like, what the heck is this? The model doesn't predict it. What is this thing here that's totally unexpected? And so through the course of several weeks, as we kept thinking, okay, what's a reasonable thing that could be in this atmosphere? What fits, what absorbs at this right color, the right wavelength of light? We finally did come up with the answer. And so what I've just shown you is here. This is the data I just showed you. We actually got much more information than that. All of these little dots here are the data we got from JWST. And so you can see we actually detected all kinds of molecules. So there's water here, and this is sodium. Again, this is carbon dioxide and water mixed together. But we did manage to ultimately identify this mystery molecule here, and it's sulfur dioxide. No one reacted very strongly, but to me that's amazing, because it's telling us that this atmosphere is not just behaving perfectly like we would expect it to have formed and then keep going. It's being influenced by the star to make this gas. And how that's happening is, so starlighting is coming in, acting on the atmosphere, breaking apart water molecules, part of that oxygen goes and hits a hydrogen sulfide molecule, which we also would expect in the atmosphere. Subsequent interactions happen until ultimately we get this molecule sulfur dioxide. We call that photochemistry because it's chemistry being driven by light from the star. And maybe that sounds wild to you, but you encounter it every day on Earth. So smog that you might see in a sunset, that is driven by photochemistry. Or the ozone layer on Earth, that's another example of photochemistry we experience. And until we made this measurement of sulfur dioxide on WASP 39b, we had never seen it on a planet outside the solar system. That's it for WASP 39b. Now we're moving to an object called VHS 1256b. And I should just note that all of these sort of hideous telephone numbers are named in a very particular way. They're named for the star, which is just a catalog number, and then this letter determines which planet around it. So B is the first planet we found around this star. C would be the second planet, and so on and so on. They sometimes have prettier names, but we tend to call them just their boring names for that reason. The other thing about this object, VHS 1256b, that it's not really a planet at all. It's something we call a brown dwarf. And so it's kind of it's in this in-between space between planets and stars. And so it's big enough that it's fusing deuterium in its core, which is heavy hydrogen. But it's not quite big enough that it's actually undergoing hydrogen fusion like our sun. And so sometimes they're called failed stars, but they're actually really interesting objects in their own right. And again, this is an artist's image, not a real image of this object. And so again, JWST was able to get this exquisite data, and so the ones I showed you previously, you just saw those little dots because the measurement's really hard to make. This is a little bit easier, and so actually this line here is not a model, that's real data that JWST was able to measure. We measured all these different molecules in the atmosphere, carbon monoxide, carbon dioxide, methane, water, etc. The exciting thing here is actually this little feature here, this little dip. It's actually the signature of silicates. And so when you think about silicates on Earth, you mostly think of rocks. But this object is hot enough that the rock material is vapor that is then condensing out like a cloud. So these are rock clouds on an object outside the solar system. Again, that's not the coolest thing you've heard today. You should just probably get up and leave. We're now going to maybe planets you've heard of. So we're moving away from these hot Jupiters, from these more exotic sounding planets, to things that we kind of think are roughly similar in size anyway, and in temperature to objects in our solar system. So these are the TRAPPIST-1 planets. This is TRAPPIST-1b and TRAPPIST-1c. And so this is part of a system, TRAPPIST-1, that has 7 planets in the system, and 4 of them are what we call the habitable zone. Neither of these planets are in the habitable zone, but some of the ones that are further out are the right temperature that we think liquid water could exist on their surfaces. So they've gained a lot of interest because people think, okay, maybe these worlds could be habitable. Again, not these two, unfortunately. We're sort of working our way out in the system, so these are the first 2 that we have data for. And so with these initial 2 objects, what's been done is we've essentially taken the temperature. If you think way, way back to the beginning of the talk when I told you about Mars, we measured the temperature at a particular part of the planet. So we measure what the temperature is on the day side. If that temperature is a little bit cooler than just if starlight were hitting it, we can infer that there's an atmosphere on the planet because it's recirculating that heat and modulating the temperature. So it's not just purely day side, purely night side, it's kind of mediating it like a thermostat. And so we measure the temperatures of TRAPPIST-1b and c, and we found that there is no such thermostat that we can measure thus far. So that means if they have atmospheres, they're very, very tiny, more akin to Mars, but probably even smaller than that, if they exist at all. There's a very good chance that they don't exist and they're just bare rocks, kind of like Mercury. Hope isn't necessarily lost for these habitable planets because they're a little bit further out. They might have their atmospheres. Those measurements are still ongoing. I should actually point out that the TRAPPIST-1c measurement came out yesterday. So this is very active research. The other 5 planets in the system will probably come out, that data will probably come out in the next year or so. And then finally, this is a planet near and dear to my heart because it is data that I have worked on and tried to explain. Maybe, and I say maybe because this is not a short thing, the first rocky world that we detected that might have an atmosphere. So this is GJ486b. It's in the constellation Virgo. So Venus is over there, Virgo's like roughly there, so you can like look that direction and wave to GJ486b if you want. It's just a little bit bigger than Earth. It's what we call a super Earth, which we think very well could have an atmosphere that is similar to our own. It's much hotter. It's about 800 degrees Fahrenheit. So again, not a habitable place, but still something we're interested in to learn if it could hold on to an atmosphere. So these are the data. They look very messy. And I just sort of want to defend JWST here because those things I was showing you earlier are much bigger planets, much stronger signals. This is the very, very cutting edge of what JWST is able to measure. This was not possible with Hubble. The resolution and the accuracy was just not quite good enough. This is just very much the frontier of measurements that we can make today. And so it's kind of messy, but we can fit models to it, which is what these 2 colored lines are. So the blue line is a water atmosphere on this planet. So again, it's too hot for it to be liquid water, but it would be in the form of steam around this planet as its atmosphere. And you can see, you know, squinting, it actually fits the data really well. It's a perfect match, statistically speaking. And so we saw this and got very excited and thought maybe we have for the first time detected an atmosphere on a rocky world outside the solar system. But we are scientists, and we try to be skeptical and thought, okay, what are the other explanations that could also explain this data? And that's what the yellow line is here. So it turns out that the stars that these very small planets orbit that we can measure with JWST are quite cooler than the sun, and they have star spots on them, just like our sun has sunspots. And so it can actually be cold enough for water to exist on the star and not the planet. And that is the scenario that's plotted in yellow here. As you can see at the wavelengths we measured, those look exactly the same. We can't tell right now with these measurements whether we've detected a water atmosphere on the planet or if we're just measuring star spots. And so my colleague made this meme for us that this is us, of course, initially all excited, and then maybe it turns out it's just the star tricking us. So that's also research that is ongoing, and I hope to have an update maybe in the next year or so to definitively determine the nature of this planet. And so this is all probably too small for you to see. But just to summarize what I've talked about here, the JWST has shown us the solar system in a whole new light, literally, in the infrared. And we've detected, for the first time, carbon dioxide on a hot Jupiter, which is something that was predicted. Great, JWST is working well. We also detected sulfur dioxide for the first time on a hot Jupiter, which was totally unexpected, although in hindsight should make a lot of sense. Just, again, the power of JWST here. We see rock clouds on a brown dwarf, and maybe we're hedging toward actually detecting atmospheres on rocky worlds outside the solar system. And I also finally just want to close with, it's not even been a year since JWST has been up and doing science. This has been 11 months since it started sending data down for scientists to use, and it's expected to go for another 20 years. So there is way more to come from this observatory, which I'm personally very excited about. Thank you all for your attention, and I'm happy to take questions. The question was, how did I get interested in this? And there's sort of like 2 answers, and one is the very sappy answer, and one is sort of the nerdy answer. I'll start with the nerdy answer, which is that I'm a really big sci-fi fan. So the idea of looking at other worlds and imagining what they could be like really appealed to me. And then the sappy answer is that I was a physics major in college, and I thought a lot about studying climate change on Earth. But to be perfectly honest, the thought of that was like kind of depressing to think about day after day. And so this lets me get close enough and develop the expertise in climate science and thinking about atmospheres while still getting a lot of the joy of it, of discovery, and not necessarily the depressing parts. And so I still do think about that, and I am still depressed about climate change all the time. But my day job doesn't dwell on it. Thank you. In the back there? So the question is, how can you have a star that can have water on it? Which is a great question. So even the sun actually sort of transiently has water on it. And again, it's not liquid water, it's water vapor. And so basically in the spots, there are these regions that are cooler than the rest of the surface of the star. And it's basically due to magnetic effects that are just causing these tiny regions to be slightly cooler, and it's just cool enough for water to exist in a vapor state before it gets dissociated again into just hydrogen and oxygen atoms. And so that does happen in the sun. We've detected it since like the 70s. And so of these smaller, cooler stars that are already cooler to begin with, it's much easier for water to exist in their star spots. You have a follow-up question, I can tell. Do I know what temperature that is? So water vapor starts to dissociate like around 2000 Kelvin, which I don't think I can translate to Fahrenheit for you on the spot. That's perfect? Okay, great. You had another question?
I've had this happen on OBS before. Okay, come on properties.
The question was, when am I going to be the professor of U of A? So my boss is actually in the audience tonight, so maybe you can ask him that question. I don't know. Other question.
Click.
In the back there, yeah.
Oh yeah, the whole thing is moving.
So the question was, you said you're close to detecting rocky atmosphere with JWST. What's needed? Why haven't we yet? The answer is in some ways time. Not every planet is going to have an atmosphere. We haven't quite figured out why some have atmospheres and some don't. We have theories. We just have to kind of keep measuring a bunch of rocky planets until we get lucky in some sense. So we've measured 4 that I know of. So, you know, the odds on that aren't actually that great. But we have data that's the telescope has taken and is sent down and is actively being analyzed by scientists around the world. So I wouldn't be surprised if we make that measurement in the next couple months. Because there are maybe a dozen rocky planets that have been observed in this first year. Fun?
So, what's the implication of detecting carbon dioxide outside of the solar system?
The question was, what is the implication of detecting carbon dioxide outside the solar system? The answer to that depends on what planet you're thinking about. If you're thinking about a rocky world, the implications are huge, because it means there's an atmosphere on a rocky world with a gas we know. Crazy exciting. We haven't done that yet. But on a hot Jupiter, it kind of tells us a couple things. It means we predicted from atmospheric models that carbon dioxide should be there. So in the one sense, it tells us that our models are not completely off the wall. We kind of know what we're doing, which is great. It also tells us something about how the planet formed. So if we can predict the correct amount of carbon dioxide, as we did, we have a sense that we kind of, more or less, in broad strokes, understand planet formation. I don't know if that train's going to totally kill us. Yes,
yeah.
It is. Cheers, everybody.
Choo-choo.
Is it coming this way? It sounds like it's over there.
There's a wall behind it.
There it goes.
questions shout, I can probably hear you now. Right here. So the question was, who gets access to the data? Who are the lucky scientists who actually have access to these measurements? So there's this sort of somewhat bureaucratic process in terms of people have a science idea, and so they write a proposal and say, hey, I have this amazing idea, I want to point the telescope at this object. And if they did a good enough job convincing their peers that the science is interesting and that the measurement is possible, they win the time and then they get access to the data. And they usually have about a year, 6 months to a year, where the data is only for them to look at and no one else gets access to it. After that, it goes public and anyone, including you all, could go online to the Space Telescope website and download the data. There are also some programs that don't have what's called this proprietary period. So really large programs where they're getting a lot of hours is meant to be a community effort. And so those data are available right away. Here.
So with the new data that you just processed for TRAPPIST-1c, not having an atmosphere, with it being a red dwarf that's blasting out those atmospheres, would it mean that the habitable zone would be further away than we thought because of the fact that that radiation blasted off 1c's atmosphere?
So the question was about TRAPPIST-1c and how the data seem to show that it doesn't have an atmosphere, that maybe it's been blasted off, it hasn't lasted. I do want to clarify, TRAPPIST-1c is not in the habitable zone. It's interior, so it's slightly too close. It's too hot that we would ever expect liquid water to be stable on its surface if it had an Earth-like atmosphere. The outer planets are the ones we think are in the habitable zone, so that's, depending how you define it, D, E, F, G. We never thought C was habitable. But that is a good question about how do these planets hold on to their atmospheres? And we do think that maybe the star is just blasting them all to heck, and so the atmosphere is being lost to space, even if it formed with one. It's also possible it didn't form with an appreciable atmosphere in the first place. And those are the theories we're kind of trying to refine by measuring all of these different planets. If we can get a census of which atmospheres have which planets have atmospheres and which don't, that can let us know about the physics that's driving those things. In the back, I thought I saw someone. Maybe not. Over here, yes. The question, do you have further? No, that's okay. So the question is, when we're talking about hot Jupiters, what does that actually mean? Do we mean just planets that are that big as Jupiter, or planets that are gassy like Jupiter? And the answer is yes. Planets that are that big have to have a really big gassy envelope like Jupiter. You can't have a solid planet that is that big. It has to have a gas layer. So the answer is they are about the size of Jupiter, which take a couple, a factor of a couple, and they are mostly gas, meaning hydrogen and helium, among other things. Question here?
What do the error bars look like on that figure model?
The question was, what do the error bars look like on that figure? I don't know if my clicker is working anymore, and I don't know which figure you meant.
The one with either there being a water-like atmosphere on the planet or water being on the star.
So the question was about the error bars on the last planet I showed, where it could be either a water atmosphere on the planet or just water in star spots. The error bars are not visible on the plot, they're so small.
Oh, okay.
So they don't really help us determine which scenario is true. We unfortunately, as always, need more data. Right here. The question was, why was this discovery of sulfur dioxide on this planet so unhinged? Why was that so surprising? And you said you're an idiot, but really the thing might be that we're idiots for not expecting it. I can see my boss, leaning here. So he and his colleague actually did predict that you would see sulfur dioxide in some cases. And so this idea was not totally out there, it just was maybe not accepted by the field as a whole, because people really like to think about atmospheres being what we call equilibrium chemistry. So kind of everything's behaving as we expect, and there aren't external sources forcing it into slightly different directions. But there's no reason to think that. Every planet in the solar system is completely shaped by disequilibrium processes, by the starlight, by the internal heat of the planet coming up and reshaping the chemistry. So in some sense it should have been expected from us. And just, we were so used to, I think, being in this land of Hubble and having very limited information, that our imaginations weren't big enough and we weren't considering all the possibilities. And so this immediately from this first observation, this very first planet that we pointed out for science, planets are more complicated than we initially were expecting, which shouldn't have been that unexpected. It's a very roundabout answer. Yes?
In the slide where you showed the two models where the water's coming from either the star spot or the planet, do you have to observe at those wavelengths where those models diverge, or are there other methods to be able to distinguish that?
It's a great question. The question was, in the figure, in the planet where it could be either star spots or a water atmosphere, where I showed data, those two observations looked exactly the same, but at shorter wavelengths, at bluer wavelengths, they look very different. Why haven't we observed at those wavelengths? And the answer is we are trying to. We have asked Space Telescope if we can go look at the shorter wavelengths. And, if you all have any pull at Space Telescope, please tell them we would like those observations. This is the last question. You have a follow-up.
Yeah, what wavelength is?
What wavelength? So they diverge the most strongly at those ultraviolet wavelengths, but Hubble is not quite good enough to make those measurements for us. But the shape of the water absorption is actually different at 1.4 to 1.6 microns, and so that's what we would like to measure, which is an instrument on JWST that can do that. So thank you all for all your amazing questions.
Thank you, Sarah. Sorry we had to cut off your questions, but it is getting late. Let's give both of our speakers one more quick round of applause. And that's it for our show tonight. Thank you so much for joining us. We will be back on the third Tuesday of July, which I believe is the 18th. So hope to see you all then, and have a good night.
I just pulled the camera out.
That's not going to shut down OBS. That's not going to.
It's frozen, but it's still broadcasting.
Brilliant. Okay, when did that happen?
9:03.
Yeah, 9:03.
Hilarious. Okay.
So I guess
Just shut the computer down.
I yanked out the
completely.
Yeah,
That's funny.
Care about
It must have been.